Hi, everyone. Okay, so again, just to take a minute to see where we are and what the point of all this is, let me write something down. So the idea, our plan, is to be able to solve a linear system of equations. So we're going to start with some linear system, and we're going to convert it to an augmented matrix. And from there, we're going to use Gauss-Jordan algorithm, which we'll learn next week, to transform that augmented matrix into a row equivalent matrix in reduced echelon. And then from here, once we have our row matrix in reduced echelon form, we want to be able to read off the solution to the initial system. So just thinking again about where we are, we talked about this before. This is what we're going to talk about right now, and this is for next week. So we're going to be talking about matrices in echelon form, and so the idea is that these are the end results of the Gauss-Jordan algorithm being applied to an augmented matrix. And so we know what the solutions to linear systems can look like in 2 dimensions. There's 3 scenarios, I guess, right? There's when you have no solutions. Then there's a scenario where you have one solution. Those look like points. And then the other scenario with a 2-dimensional system is infinitely many solutions because the lines are really the same line. In 3D, and I'll refer you back to those other pictures. I'm not going to try and draw them again. But in 3D, there's also just 3 different possibilities. One is to have no solution. One is to have a unique solution, so just one point. And the last possibility is having infinitely many solutions. And in the case of 3 dimensions, that infinitely many can look like a line, or it can look like a plane. Right? If all the planes overlap, then that's the infinitely many points on the plane are the solutions to the system of equations. So when we have just one solution, we know how to express this, right? It's going to be x1 comma x2. It's the coordinates of a point on the plane or a point in space, right? And we're filling these in with numbers. But how do we write this down? Right? How do we describe a collection of infinitely many different solutions? Well, we're going to see how to do it in just a minute. First, though, we need a little bit of terminology. So here's a matrix just so I can point to something while I'm writing down the definitions of these words. So this is a matrix already in reduced echelon form, and we can see that right, by looking at these pivots, right, the leading entry in each row. There's no rows of all zeros, so there's nothing to worry about there. And the leading entry of each row is a 1, and if I look above and below the ones, so if I check out those pivot columns, they look like pivot columns, right? They're supposed to have a 1 in them, and then the rest is 0. So this is in reduced echelon form. Now, remember also that each one of these columns, when we're thinking in the context of a linear system, each one of these columns corresponds to a variable. And these are the coefficients stored in there, and then this vertical line is like an equal sign, and then there's a right-hand side constant. So the terminology that we're going to use is talking about the variables and characterizing them based on the properties of the corresponding column in the augmented matrix. So we say a variable is basic if its column contains a pivot. So basically over here we have 3 variables that are corresponding to pivot columns. So x1, x2, and x4 are basic. And then free variables are variables that are associated with non-pivot columns. So like this 620 and this 052, those are non-pivot columns. So we can say x3 and x5 are free. So once we have this information and can identify the basic and free variables, we do actually have enough information to write down what we call the general form of the solution. here's how that works. So we know that this is a 5-variable system, so we need to have something assigned to, each one of these 5 blanks. If there were no free variables, then we would have all numbers, and we would write down a 5 tuple describing the point of intersection of a bunch of hyperplanes in 5-dimensional space. But in this case, we have some free variables. So x3 and x5 are free. That means that those 2 variables are just going to get filled in by themselves, just the actual symbol x3 and x5. These are not placeholders for numbers. And the idea is that the rest of these, the basic variables, are going to be expressed in terms of the free variables. So basically, these guys are going to be functions of x3 and x5. So where are we going to get those functions? And the answer is we're going to get them from these equations, the equations that are this linear system. So I'm going to start at the bottom. The last equation says that x4 plus 2x5 is equal to 5. So now if I move this over, I have x4 is equal to 5 minus 2x5. This is going to be the expression that I put in in the place of x4. That's an expression in terms of x5. See, now for x2, that equation says x2 plus 2x3 plus 5x5 equals 4. Again, the only variables that are showing up here besides x2 are x3 and x5. Those are my free variables. So I can write this as, 4 minus 2x3 plus 5x5. And that is what's going to go in place for x2. And finally, the equation for x1 says x1 plus 6x3 equals 3. So that means x1 is equal to 3 minus 6x3. And that's what we're going to fill in the x1 blank. And this now is our general solution. I'm going to write it down again over here, so just clean it up a little bit. Okay, so that seems like it might have been hard. Let's try another one. After you see a couple of them, it starts to get much, much easier. Okay, so let's look at this one this time. The first thing I'm going to do is notice which are my free variables and which are my basic variables. So it looks here like x1 and x3 are basic, and x2 is free. So let's write down the general solution here. So this is a 3-variable system. So I have 3 blanks to fill in. If I were going to write down a point, it would take these 3 blanks. x2 is free, so that guy just goes in here. And now let's look at the other equations to find expressions for x1 and x3. The bottom equation says that x3 is equal to 8. Well, that's nice. That's not much of a function at all, right? I just can put in the 8. And the first equation, the top one, says x1 plus 2x2 equals 3. So x1 is equal to 3 minus 2x2. And that's our general solution. Now, if I plug in some number for x2, like say when x2 is equal to 0, if I plug that number in, I'm going to get, I'll get 308. Now, this is a point on the line of intersection. If I plug in other numbers, I'll get more points on that line. So if I plug in x2 equals 1, I'll get 1, 1, 8. And that's another point on the line of intersection. So this is what you need to practice so that you'll be able to read off the solutions from the echelon form of matrices when you, after you perform the Gauss-Jordan algorithm to transform a initial linear system into something that's in reduced echelon form that has the same solutions as the original system.